Okay, let's go on to something that's pretty cool now. So this is going to use a combination of the chain rule, which we used in the last section, the logarithmic rules, which we used in the last section, paired with the logarithmic properties, like multiplication separates to addition, division, subtraction, bring the powers down in front. And we're going to use implicit differentiation. So these are really what I consider truly badass problems, that you can really take some derivatives of nasty functions and use the tricks that you know to make it so it's not so hard to find the derivative. That does not mean the derivative looks nice, it just means it's not that difficult to find the derivative. These are going to look nasty, nasty, nasty. So what's the idea? What if someone said, find the derivative of the function y equals x minus 2 quantity squared all over the square root of x squared plus 1. So if you imagine here, you would have to do a quotient rule, and each one of the individual parts would require a chain rule as well. So it'd be a quotient rule with 2 chain rules involved, and I'm telling you, you don't need to do this. Why? If we have an equation here, one thing we could do is we could take the natural log of both sides. So because these things are equal, we have y equals x minus 2 quantity squared all over the square root of x squared plus 1. Because those two things are equal, one of the properties that I can do, as long as these numbers are positive, which we're going to assume, is I can take the natural log of both sides of this equation. Why would I want to do that? Well, on the right-hand side, I can do a lot of simplification. On the left, I would have the natural log of y, and on the right, I'm going to do a bunch of stuff. So I know division turns into subtraction, but I also know I can bring those exponents down in front. So the first term would be the natural log of x minus 2, technically squared, right, but I'm going to bring that 2, that exponent, down in front. Division turns into subtraction. I'm going to have the natural log of x squared plus 1. Technically, it's the square root of that, or that to the 1/2 power, right, but I'm going to bring that 1/2 power in front. So again, I used division, I separated as subtraction, I brought the 2 down as the power in the numerator, and I brought the 1/2 down in front as the power from the radical. So now I have this function right here. Now what can I do? Now I can take the derivative with respect to x of each and every one of these terms. Okay? Because they're equal, their derivatives are equal. Well, what's the derivative of natural log of y? Remember, it would be 1 over, let me get black. It would be 1 over y times y prime using that chain rule. What's the derivative of 2 times the natural log of x minus 2? Well, it's 2 times 1 over what you see, 1 over x minus 2 times the derivative of the inside. So we need to multiply times the derivative of x plus 2. We have minus 1/2 times the derivative of the natural log of x squared plus 1 would be 1 over what you see, x squared plus 1, times the derivative of what you see. So we still need to find the derivative of x squared plus 1 using the chain rule, right? So what's the derivative of x minus 2? That's simply just a 1. What's the derivative of x squared plus 1? That's simply a 2x. Now let's do some simplification. On the left, I'd have y prime over y equals. On the right, I would have 2 over x minus 2. And then I would have minus, notice these 2's would simplify. And then I would have x over x squared plus 1. Okay? So I need to solve for y prime, don't I? Well, that would tell me just multiply both sides of the equation, the entire equation, by y. And if I do that, I'd have y prime equals 2 over x squared x minus 2 minus x over x squared plus 1 times y. But now what I can do is go back to my original function at the way beginning, and plug that in for y. So this is going to be y prime equals, let me use black, y prime equals 2 over x minus 2 minus x over x squared plus 1, that entire quantity, times x minus 2 quantity squared times the square root of x squared plus 1. Okay? Is there more math I can do? Oh, I'm sure there is. Do I care about doing more math? No, I do not. I'm going to give you full credit for this right here. What would they do in the textbook? Most likely in the textbook, they're going to get a common denominator for these types of things, okay? So for instance, they're going to multiply this times x squared plus 1 over x squared plus 1. They're going to multiply this by x minus 2 over x minus 2. Combine these terms and then see if you can combine any more of the terms and simplify. And yeah, you can. I know you can because x minus 2 is going to be a factor. But quite frankly, I do not care. If you got this far and you were able to solve for y prime this far, I'm going to accept that as your answer for this problem. So I'm okay with this. The textbook takes it further because the textbook gets a common denominator and tries to simplify. No need in my class for you to do that. Okay, let's look at example 10 here for logarithmic differentiation. Look at this equation. This is really messed up function. It's exponential in the sense that there's an x in the numerator, but there's also an x in the denominator. So what in the heck do you do when you see something like this? We have no derivative rules to do this, so you could not find the derivative of this the way that it is. So what's the trick? Again, when it's nice and ugly like this, take the natural log of both sides. So we're going to say the natural log of y equals the natural log of that. Okay, and then remember, when you take the natural log of it, x to the 2x, you can bring that exponent down in front. So here we'd have the natural log of y equals 2x times the natural log of x, right? Now that we have that, we can take the derivative with respect to x of both sides. On the left, the derivative of the natural log of y is 1 over y times y prime using the chain rule, right? Again, the goal is we're going to solve for y prime. On the right, we need to use the product rule. The first function is 2x. Derivative of the second function is the derivative of natural log of x, which is simply 1 over x, plus the second function, which is the natural log of x, times the derivative of the first function, while the derivative of 2x is just a 2. Let's go ahead and clean this all up. So 1 over y times y prime is y prime over y. 2x over x, those x's simplify, you're left with just a 2. And then we have plus 2 natural log of x. So we're close. We need to solve for y prime. So what I'm going to do is I'm going to multiply both sides of this, or both sides of the equation, the entire side, use parentheses, times y. On the left-hand side, I end up with y prime. On the right, I have in parentheses 2 plus 2 natural log of x. I could factor out the 2 if I wanted, no need. And then I'd have a y. But then the key again is to back substitute for the original function y. The original function y was x to the 2x. So what I'm getting is y prime equals 2 plus 2 natural log of x times x to the 2x. And there we have it. So we would have 2 plus 2 natural log of x. Again, you could factor out that 2 if you wanted, no need, times x to the 2x. And there it is. So it says here are some guidelines for using logarithmic differentiation. In general, use logarithmic differentiation when differentiating a function involving many factors or a function having both a variable in the base and a variable in the exponent. So I really like this second example, example 10, because this is the only way you could differentiate that function. It has a variable in the base and in the exponent. But you could also use logarithmic differentiation on a rule like on the example 9 right here, where if I put that on the test, it's open reign. You could use the quotient rule. You could bring the denominator up into the numerator and use the product rule, or you could take the log of both sides and use the log rule. So I beg of you, please read the directions on the test. If it says just find the derivative, you could have used any one of those methods for method 9. But if it says using logarithmic differentiation, you must take the log of both sides, you must do the derivative, and then you're going to multiply both sides by y, and then at the end you always back substitute for y. So never forget to back substitute for y like we did in both of those problems. Okay? So read the question. If it says using logarithmic differentiation, you must. If it's a problem like example 10, you must use logarithmic differentiation. Otherwise, do what you want.